There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium. And
you can sing it.
Neptunium, germanium, and iron.
You can dance it.
Ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium.
You can even play it. So why then is it so hard to make sense of the periodic table? The simple answer? Because it's the blueprint for everything. A chart that sorts every known element and catalogs every fundamental unit of the universe according to its atomic weight, creating the basis for chemistry, physics, and other scientific fields. But for many people, trying to read the periodic table is like understanding another language, and in many ways, it is. That's in part why UNESCO and other groups are hoping 2019, the International Year of the Periodic Table, will shed light on the importance of the chart and the critical role it's played in an unknown number of scientific achievements since its creation 150 years ago.
Marie Curie carried on the work alone and was awarded the Nobel Prize for an unprecedented second time.
So what makes the periodic table so important, other than giving society acronyms like H2O?
The periodic table is extremely foundational.
It's important in every way you can think of.
In 1869, Russian chemist Dmitri Mendeleev essentially discovered a cheat sheet for scientists.
Yeah, it's a very good way of thinking of it, actually. Look at some element, you may not have never heard of it, but if you can look at it and see where it lies with respect to something that you know, you can know something about how the properties will relate.
According to the International Union of Pure and Applied Chemistry, the table popularized by Mendeleev enabled scientists to predict the appearance and properties of matter on Earth and in the universe.
As I teach budding chemists, I actually use the word chemical intuition. As chemists, we develop this intuition so we can look at the structure of a molecule and we can have some idea of what we think its reactions would be, some idea of what we think its properties would be. We use that intuition to predict what we think will happen and then experiments to confirm or sometimes they surprise us.
Since Mendeleev's discovery, a rapid and intense expansion of scientific achievement and knowledge has occurred over the last century and a half. That's not to say chemistry did not exist prior to Mendeleev's discovery. Chemical reactions of atoms fusing under extreme heat led to the creation of the solar system 4.5 billion years ago. There was the discovery of fire as early as 1.7 million years ago. Experiments smelting copper with tin began the Bronze Age in 3300 BC, which was followed by the Iron Age 2,000 years later.
A lot of things have to happen before a periodic table is even thinkable, and then once you have a table, it allows you to think other things. The biggest transformation happens in the 1770s and 1780s, which is what's often called the chemical revolution, which is based in France and Britain, and is that what we now consider the discovery of oxygen and a new theory of burning, and therefore a new compositional view of how matter is made. In the 1820s and 1830s, people start experimenting very heavily in how to synthesize and create new organic chemical compounds. Those two transformations set the stage for what happens in the 1860s with the chemical elements.
There was as many as 6 chemists during the 1860s racing to develop a chart to outline periodic law. A law stating that the elements, when listed in order of their atomic weights, now of their atomic numbers, fall into recurring groups so that elements with similar properties occur at regular intervals. Amid the feverish rush to define how periodic elements related to each other, Mendeleev's genius came to him in a vision. "I saw in a dream a table where all elements fell into place as required. Awakening, I immediately wrote it down on a piece of paper. Only in one place did a correction later seem necessary." Mendeleev's vision began with 63 elements, which at the time were all that were known to scientists. Even more daring, Mendeleev purposely left gaping holes in his chart to make room for elements he guessed to exist but hadn't been discovered.
His chart it's done in ignorance of the other charts. He doesn't really know other people are working on them, and that's true of almost all of these people. Mendeleev makes a big assumption, which is that all the gaps are filled. That if you see a gap in the table, there should be an element there. There's actually no reason in that time period to assume that would be true. Like, Maybe there just are 63 elements. Maybe there are only 70 elements. It's hard to know how many there would be. And so he tries to use the spaces in the table and some inductive reasoning to predict new elements that have not yet been discovered. And that's not just unique among the periodic tables, that's pretty much unique in chemistry. People hadn't tried to do that kind of thing before.
When the elements scandium, gallium, and germanium were discovered, filling in the gaps left by Mendeleev, it cemented the belief that he discovered a law of nature and staked his claim as the father of periodic law. Since its inception, Mendeleev's chart has ballooned to 118 elements, including Mendeleevium, discovered in 1955 and named after him.
His tables go through a bunch of mutations. It starts out on what we would call its side. It's tilted over, it's expanded out. But that's not the big change. The biggest change is that starting from the 1920s through the 1940s, the understanding of how atoms are structured moves entirely to quantum theory, which is an explanation for how the electrons, which are responsible for the chemical properties, are arrayed in shells or clouds outside of the nucleus. So that transformation has really altered our understanding of how matter is organized and how it works at multiple scales.
In that time, the science has changed our world drastically, both for the betterment of society and in some cases for worse. We harnessed the power of energy, created medicines and cured disease, developed technologies that have allowed us to travel into space, and designed gadgets that allow us to store nearly as much information in our pockets as the periodic table teaches.
One of the interesting things about the periodic table is a lot of the products that we think about as being bad, like DDT or PCBs, a lot of these compounds contain halogens. The people that were making those chemicals weren't like mad scientists, like I'm really looking forward to ruining everybody's life. They were really doing something great at the time. We just didn't have enough understanding. Whereas nowadays, we're trying very hard not to make chemicals that are quite so persistent. And so chemical manufacturers use this knowledge of the periodic table to try to come up with molecules that will be just as effective, just as safe, but will degrade through natural processes in the environment and not cause these problems for future generations.
As scientists strive to develop technologies and make new discoveries, it begs the question, is the table complete?
There's a lot of theoretical debate about what the most heavy element you could construct is, even theoretically, let alone practically figuring out how to do it, because they're incredibly unstable when the nuclei get to be so big. Will somebody do that? I expect yes. But it's unclear how many more elements you could have that would be around even long enough for us to know that they were there.
The chemistry is still an experimental science. But ultimately, we still need to do experiments to see what really happens. There are still lots of things that we don't know. That's what keeps us going, in fact, as chemists. And if we knew everything already, what else is there?